Hello, this is Powell, and this is another demonstration video. This one follows after the last one that I posted on the Sumo competition robot, and there's really nothing much more that has been done since then. The only major accomplishment is the implementation of the Exponential Weighted Moving Average filter, which is only one line of code, and it's essentially a weighted average between current input and the previous output value. So it's pretty simple, and essentially it's needed for filtering out the noise from the IR sensors, as you can see here. So basically, one of the previous videos I had something similar to this, where essentially both IR sensors are connected to the I2C mux, and they're both being triggered for their IR reading. So I move the my phone closer. I'll put my hand over one. As you can see, IR1 goes up. If I move it over to the second one, IR0 goes up a little bit higher. But in addition to that, I'm also doing some benchmarking basically, just to figure out how long this entire operation is taking. So for each of the IR sensors, where it says cycles, for IR0 and IR1, essentially that's a number of core timer cycles it's taking to complete the filter operation. The reason why I'm trying to test specifically the filters because I've been debating whether or not I should use floating point arithmetic or if I just should default to fixed point. And to be honest, the fixed point is just way faster. When I did it, it was like 3 cycles to complete a single multiplication operation with decimals, basically 16 real bits and 16 decimal bits is what I used, and it took like 76 cycles of a floating point. So what you're seeing now is basically how long it takes for the whole operation to take. Basically, what you're seeing now is how long it takes for the whole filter operation to take using floating point values. And even though it's much slower, I decided to just to use it just for the convenience sake, so I don't have to worry about doing much shifting at all. Mainly because I want to say that I'm gonna have plenty of time left over. The goal is to make sure I get a new output every 20 times a second, so 20 hertz. And the thing that takes the longest by far is really how long it takes to get the readings from the sensors in the first place. Currently, I really haven't changed much of the sensors. I haven't increased the current or changed the number of measurements per second, although I don't think that should affect anything. I am using the VCNL 4010, and I don't believe changing that, like based on how I'm using the sensors, I don't think they'll actually change much, but I'll have to relook at the datasheet. Currently, with the current configurations, it takes 72,000 clock cycles, and by clock cycles, that's the core timer, which basically runs, each time the core timer ticks, it's like 2 system clocks, and the system clock runs at 80 megahertz. So, long story short, the whole operation takes approximately less than 2 milliseconds to read from both the sensors. So, really hoping with threading I can actually save a lot of time, because most of the time spent reading from the sensors is just polling them. As I mentioned in an earlier video, for whatever reason I could not get the interrupt to work, at least the way that I needed it to. So I'm just doing polling, and I'm hoping by running multiple threads I could be performing the control algorithm and other stuff while also reading the next values from the sensors. And hopefully I can do that 20 times per second. So, spoken to one of my professors, and it seems like I might just go with the PID controller, but might do something else. But PID controllers are by far the simplest, and sometimes good old Occam's razor is the best course of action. But nothing much more to say in this video. I'm hoping by the end of this week I have the first prototype finished with my mechanical engineering friend Dimitri, and hopefully we have some videos on that. And this concludes this video.